Hello, and welcome to this lesson introducing solving systems of linear equations. We're going to look at what the solution to a system, what is a system of linear equations, basically any two or more equations taken together. The solution on a graph, what does it mean? And how to use, we're going to just do an introduction to the method of substitution and the method of linear elimination. So we're going to be utilizing some graphing apps, Desmos, most commonly here. And we'll be doing a little bit of algebra as we go. You should stop the video anytime you don't understand anything. Rewind a couple of times. I will tell you to stop and ask you to use some time and try a problem before I do the solution. So let me just pick up a pen here. So we're exploring systems of equations through graphing. This is found in your week 4 folder. It says Introduction to Solving Systems of Linear Equations. We're going to consider these two equations, x plus y equals 5 and x minus y equals -1. And we can't solve x plus y equals 5. We could write y equals 5 minus x or x equals 5 minus y, but we can't get a number for it because there's two variables. Same thing for x minus y equals -1. There are infinite solutions to a line. Anytime you graph a line, each point on it represents a solution. Each point on this line, x plus y equals 5, would represent a solution to this equation. Each point on this line would represent a solution to this equation. And there are infinite number of points on the line, so there are infinite solutions when you only have one. But when you're given two equations, it's called a system. And what you're trying to do is find the x, y combination that will make both true at the same time. Like if I put x, I have to replace x with a number here and y with a number here, and I use those same numbers here, it results in two true statements. So to exemplify what I mean by that, we're going to try putting in, sorry, I want to change my pen color a little bit here. I'm going to try putting in x is 2 and y is 3. Now, remember, whenever you're given a coordinate pair, the first one is x, the second one is y, unless you're told otherwise. So I'm going to replace in the first equation, x is 2, y is 3. And the question is this true? Does that equal 5 for this equation here? Yeah, it does. And then in the second equation, x is 2, y is 3. Does this equal -1? Yeah, it does. So this point is a solution to both of these lines. So it is a solution to the system of equations. So the solution to a system of two equations with two variables is a point, x, y. Now, if you go into 3 dimensions, x, y, z, you would have x, y, z, but we're not going to get there. Or some people would write x equals 2, y equals 3, and say that's the solution. The mathematical notation for writing that is as a point. So both of these simplify to a true statement. If I put the point x is 2, y is 3 into the first equation, I get a true statement. If I put in the second equation, I get a true statement. So that is the solution. And it turns out, anytime you have two equations and two unknowns, you can either find a point that solves it, or you find that they're actually the same line, so there's still infinite solutions, or the lines are parallel and there's no points in common, so there's no solution. That's what we're going to investigate more here. So this does simplify to a true statement. Now, I just did this. I already did this. Replace x and y in the second equation with 2, 3, and simplify. I did that right up here. 2 minus 3 equals -1. So the solution, so if I ask you, is 2, 3, another way to ask this question is the pair 2, 3 a solution to this system? You would do what we just did. You would check to make sure it made both equations true. So the answer here would be yes. X equals 2, y equals 3 makes both equations true. That's basically what you're doing when you look. So, I've given you the solution and shown you what it means or how it works out. Finding the solution is what we're going to be working on. You're going to be given these two lines and asked to find what combination of x and y make it true. Now, there are infinite combinations, so guess and check is not your best friend here. There are methods for doing this. The simplest method, if you have a graphing utility available, is to graph both and find the intersection. So we're going to go to Desmos here for a moment and take a look at, I've got x plus y equals 5 and x minus y equals -1 ready to graph. So here we are, x plus y equals 5, x minus y equals -1. So the red line is x plus y equals 5. And if we found the slope of that line either by putting this in the slope-intercept form, if I subtract x from both sides, I'd have y equals -x plus 5. I'd see slope is -1, so it makes sense that the red line goes downward. And then the blue line is x minus y equals -1. This point right here is 2, 3. So on the red line, there are infinite solutions. 0, 5 is a solution to x plus y equals 5. 5, 0 is a solution. This point here, it looks like 3, 2 is a solution. So any point I click on in this red line is going to be a solution. And for the blue line, any point I click on here is going to be a solution to x minus y equals -1. So it looks like the point 3, 4 will work. The point 0, 1 will work. The solution I'm interested in is the one that is a solution to both of them, and that is found as the intersection. 2, 3 is the solution to this system of equations because it is a point that exists on both lines. Any point on a line is a solution to the two-variable equation. When you have two two-variable equations, the point that appears on both lines is the solution to the system. So if we can just graph them both and find the intersection, we can find the solution to the system. That's not always that easy. We don't always get nice round integers. We don't always have the technology available. Plus, further on in math, there'll be fewer numbers than this, and you'll need to know some other algebraic methods. But this is the graphical method of solving a system of equations. Let's go back to our worksheet. And so we found the intersection was 2, 3. The point was 2, 3. No surprise there. That's what we see in the graph. So the point the two lines intersect is the solution. Now, let's take a look at 8x plus y equals -4 and x plus y equals 3. Let's find out where they intersect. So I'm going to turn those on and shut off our first lines. I had these all prepared, so you didn't have to watch me type. So the green is 8x plus y equals -4. The blue is x plus y equals 3. So I'm looking for this point where they intersect. I'm not, this is the y-intercept of the blue line. That's great. That's a 3. That's not, I'm interested in the point they have in common. The point is the point is -1, 4. So when I go back here, I see that I have the point -1, 4. So now replace x and y in the first equation with the values I got. So I get 8 times -1 plus 4. And I want to see what that equals. I want to see if it equals -4. So I get -8 plus 4 equals -4. So it works there. It results in a true statement. Yes, it does. Now the other piece of my system, I think it was the green line in the graph, was that I replaced the x with -1, I replaced the y with 4, and I do indeed get 3. That also works. So the point of intersection does tell us the x and y values that will make both equations true. So that is a way to use intersections to solve. We will not be doing a lot of that because it's hard to graph by hand, but that is one way to check your work maybe. So it results in a true statement. So what's the point? What you should notice is the point of intersection of two lines or any two functions. You could use things that are nonlinear, but we're just dealing with lines. Gives the values of the variables that will make both equations true. That is called the solution to the system of equations. If you're given a point and asked if it's the solution to the system, you just replace the x's and y's in both equations and see if they're both true. If only one of them is true and the other one is not, it's not a solution to the system. It has to make both equations true. So that's a relatively simple way to find the solution to a system of equations. So, and here's problem 4. I'm going to encourage you to go into Desmos, stop this video, go into Desmos yourself. You log in www.desmos.com and type both of these lines in. On the side, you'll have, and I'll show you here. Over on this side, now I've typed everything in already. You will get some blank boxes, and you start type your equation just as you see it. So stop the video, type those in, and come back, and we'll take a look. I already have these ready to go. So the system we were looking at was negative 1/3 x minus 3. It's one line. Y equals negative 1/3 x minus 3. And x equals 3 is the other one. So there's no y in this one. But that's okay. That means any value of y will make this true. But you need to find the value of y that also makes this true. All right, stop the video. And I assume you've stopped and you've come back. So let's go to Desmos and look at these lines. I want to point out a couple of other things. So this is our new one we're doing here. That was what we just did. Let me shut those off. So to turn on and shut off graphs, you just click on them on the left. I set these up ahead of time. Now, I want you to notice negative 1/3 x minus 3 equals y is right here. Now, that is in slope-intercept form, just with the y on the other side. So the slope is negative 1/3, and indeed it goes down to the right. That makes sense. X equals 3. You read that x is always 3. That is a vertical line. Students often want to turn that sideways because the x-axis is horizontal. No, it means every point on your line has an x-coordinate of 3. Therefore, it must be a vertical line like this. This red line is x equals 3. You x equals 3 here, and you pick. So I tell students, put a point at x equals 3 on the x-axis. And then which way do you go? Well, make up another point where x is 3, like say 3, 2. Well, if I were to graph 3, 2, I'd be up here. Now you see your line goes this way. Here's my intersection, right down there for the solution. 3, you would expect x to be 3 because that's the only value of x I'm going to find in the red line, negative 4. So I get 3, negative 4 is my solution. And if I put in x is 3 here, negative 1/3 times 3 will give me negative 1. Negative 1 minus 3 does indeed give me negative 4. So for this one here, we had 3, negative 4. Stop the video and try this next one. Y equals negative 1/2 x minus 3, and y equals negative 3x plus 2. We're going to solve that by graphing. Stop the video. Okay, you're back. I assume you're either not actually using this to full value or you've already done the problem. Hopefully you've already done the problem. Let's go take a look at it. So y equals negative 1/2 x minus 3, y equals negative 3x plus 2. So these are both in slope-intercept form, and they both have negative slopes. The blue line is not quite as steep as the green line. Those are some observations to make. The green line crosses the y-axis at 2. The blue line crosses the y-axis at negative 3. Those are some review points. But where is the intersection? It looks like it's right. And if you click on this, it gives you a point, 2, negative 4. So 2, negative 4 is my solution when I do this by graphing. And if I were to check these, if I put 2 in here, negative 3 times 2 plus 2, does that equal, does negative 4 equal that? Yes. And does negative 4 equal negative 1/2 times 2 minus 3? Well, I have a negative 1/2 and I'm multiplying by 2. You multiply a fraction by its denominator, they reduce. So it does work. So I found the solution by graphing. Now, let's find the solution to number 6 by graphing. Stop the video and type in 5x minus y equals 1 is one equation. And you don't have to make a long list like I did. You can just keep replacing. And then y equals 4 is the other equation. Stop and come back when you're done. All right, you're back. So this is my next pair. So I have 5x minus y equals 1. That's this blue line, according to this legend here. The black line is y equals 4. You can barely see it because it's on a grid line, but y equals means every y coordinate is 4. So look at the points in this line. I have negative 2.014. I have, no matter where I click on that line, the y coordinate's going to be 4. So again, y is always 4. I tell students, put a point on the y-axis at 4. and then make up another point. Oh, let's make up, oh, I can't write on this, sorry. Make up the point x is 2, y is 4. And I graph that and I see the line goes sideways. Y equals cuts through the y-axis. It's not parallel to it, it's perpendicular to it. So y equals is a horizontal line. Y is always 4. Tells you the height of your graph is always 4. Y gives you the height. X gives you the side-to-side location. Now, to finish solving our problem here, I'm looking for this intersection. Looks like I have x is 1, y is 4. Now, the other way I could have solved this without a graph is I just could have taken this y equals 4 over here and put 4 in for y there, and that would have allowed me to find x is 1. We're going to talk about that when we do substitution in a moment. But by graphing, this pretty quickly comes out to be the point 1, 4. So that one was the point, oh, not that one. I'm in the wrong one. This one was the point 1, 4. And of course, you expect the y to be 4 if that's your only choice in this one, because y equals 3 would not be a solution to this. The only solution to this, x equals anything will solve this, but y must be 4. Here, they have to work in combination to come out to a 1. The combination that has y is 4 as well as the x that will help you get 1 at the end is x is 1, y is 4. So I'm going to encourage you to try these others by graphing as well and shorten the video a bit. I'm going to skip number 7. You can take a look at that one yourself and you can check that one yourself, but let's take a look at number 8. 2x plus 3y equals negative 9 and 2x plus 3y equals negative 12. So that was these two down here. Okay, so 2x plus 3y equals negative 9 is the green, and 2x plus 3y equals negative 12. And I feel like, if I don't see an intersection, maybe I need to keep looking. No matter where I look, these lines are not getting closer together. That is because these lines are parallel. When you have parallel lines, there is no value of x and y I can put. Once I pick a value of x and y, I get a number for this. And that number, if that number is negative 9, it's never going to be negative 12 with those same x's and y's. If I were to calculate the slope of each of these lines by either doing the negative a over b, negative 2 over 3, I'd get negative 2/3 as the slope. Or I could put the line into slope-intercept form and I would get negative 2/3 as the slope. Lines with the same slope are parallel. Parallel lines never cross or never intersect. Therefore, there is no solution. You can get no solution to this system of equations. Because the slopes are the same, these are parallel, and there is no intersection. They're parallel with a different y-intercept. If I solve this one, and you can do this out yourself step by step, if I isolate y for this one, I get y equals negative 2/3 x. So I would have divided the negative 9 by a 3 minus 3. Here I get y equals negative 2/3 x minus 4. They have different y-intercepts, but the slopes are the same, so they are parallel. And if I look at that, the slope of the green line is the y-intercept of the green line is negative 3. The y-intercept of the blue line is negative 4. All right, so that's solving by graphing and what happens when you get parallel lines. That is a weird one. There are two, I'm coining the phrase weird here. Both of the strange solutions, either the no solutions, this is called no solution because they are parallel. And the other strange one is when you get the slopes are the same and the y-intercepts are the same, and you're really given what looks like two lines, but it's really the same line. That will give you infinite solutions. That's the one we're going to look at next. So, and here I already did this. I wrote these both in slope-intercept form. The slopes are the same, the intercepts are different, so they're parallel. Same slopes, but different y-intercepts will have no solution. That is key to know. These are the trick questions, the ones that aren't common. Like I didn't get numbers. What happened? Now, here is another x plus y equals negative 9 and 3x plus 3y equals negative 10. Let's take a look at that. I do not actually have these set up in Desmos, but I'll do that quickly. And you can see my other lines are still here. I can shut those out. And here, 3x plus 3y equals negative. Whoa, that says xy. It'll graph that, actually. That's not what I want, though. 3y equals negative 10. These two lines are, again, parallel. If I find the slope of each of these lines, I'll find it has a slope of negative 1, but they have different y-intercepts. No solution. Okay? So, now, what if I change this up a little? I have x plus y equals negative 9, and 3x plus 3y equals negative 27. Watch what happens. I just changed this negative 10 to a negative 27. So this negative 10 is now negative 27. Wait, where'd the line go? Where'd it go? I'm going to shut that red line off. Oh, look. It's right on top of the black line. They are the same line. And what you might notice is that if I multiply x plus y equals negative 9 by 3, I get 3x plus 3y equals negative 27. If I find the slope and the y-intercept of each of these lines, however I do it by putting it in slope-intercept form, it turns out both lines will say y equals negative x minus 9. They both have the same slope and the same y-intercept, so they're the same line. If a line is two lines have the same slope and the same y-intercept, they are the same line. So this is a case where you get, oh, sorry, I'm clicking on the wrong things here. This is a case where you get infinite solutions. Because I notice if I were to multiply this whole equation by 3, I get this equation. They are the same thing. Okay? The other thing I could notice is if I turn this into slope-intercept form, and I do the same thing here, I would do 3y equals negative 3x minus 27, and divide everything by 3. I would get y equals negative x minus 9. They are the same line. The same line is infinite solutions because I'm back to only have, it's like I only really have one equation. Okay? Just putting the equation in a different form doesn't give you a new equation. It gives you the same relationship expressed differently. So this is one line. So there are infinite solutions. They intersect at every point. Okay? So that's the other special case. So when the slopes and intercepts both are the same, you have infinite solutions. When the slopes are the same of the two lines in the system, you have one of these strange cases. If the intercepts are the same, you have infinite solutions. If the intercepts are different, the lines are parallel, and you have no solution. Okay? That's, this bold is the bottom line to remember there. All right, so here's some others that will do that kind of strange thing to you. What I notice here, I'm not going to go and do these by graphing, but if I multiply this first equation here by 5, I get the second equation. So that tells me they're the same line. There's going to be infinite solutions. You will see just one line when you're finished graphing, and you'll be confused, and you'll start turning off one line or the other to see what you did wrong. They are the same line. And it's if you solve this for the slope and the y-intercept, you'll find they have the same slope and the same y-intercept if you solve each of these equations and put them in slope-intercept form. So if one equation is a multiple of the other, if I can take one equation and multiply, or if I could take I could take this second equation here and divide it by 5 all the way across. I would get that. A multiple, that's the same as multiplying by a fifth. So if one equation is a multiple of the other, you end up with infinite solutions. That brings us to, like, graphing. It's not always quick to graph. We don't always like to graph. We look at math 4 ways. One of them is graphically. Another one is algebraically. We also look numerically, which would be your guess and check method, and verbally, which doesn't really apply as much to this. But we're going to look at the algebraic way. You have more lessons that go into further depth on this, but this is usually a student's favorite, elimination or linear combination. So if we go all the way back to the first question we did, we had these two equations. So basically, you can add the two equations together. So x plus y equals 5. X minus y equals -1. So to this side of this equation, I'm adding an x minus y. To the other side, I can add the -1 because I'm told to do the same thing. It's okay to do that. So I add both equations. I line up the x's, and what's nice about this one is when I add a y with a -y, it goes away, and now I'm left with one equation, so I can find x. I would solve this for x. I would get x equals 2. Then I would go back into either of the equations. I'm going to pick the first one, and I'm going to replace x with 2. So I added the two equations together to eliminate, which is why we call this elimination, one of the variables. And I'm going to replace, I found x is 2 that way. I replace it in one of these to solve for y. I subtract 2 from both sides. I'm trying to show you good form for work here. Y equals 3. I get the 0.23. If I want to check my work, I can put it in here. And indeed, this does work. So I see that I have a plus y and a minus y. I add them up. You can also subtract. You can multiply one equation by a number and then add it to the other, or multiply both equations by different numbers and add them together to eliminate one of the variables. When you go into the more detailed lessons on elimination or linear combination, you will see all of that done. The other method will be called substitution. You may have seen this before. Most people, when they learn elimination, like it, at least on the easier problems. Like on this problem, you would use elimination because you have a plus y and a minus y. It falls out real quick. But the other thing you can do is substitution. Pick one of the equations to work with first. This is the first equation. I'm going to solve that for x. So I had x plus y equals 5. I'm going to subtract y from both sides. This is solving a literal equation. And I get x equals 5 minus y. I don't have any, I had 2 letters, so I'm going to have letters in my answer. This is why we solve literal equations too earlier. So I'm told that x is the same as 5 minus y. So I can use that 5 minus y and replace this x with it. So now I get 5 minus y instead of this x. So I'm working with the second equation now. So you rearrange one of the equations to solve for one of the letters. I could have solved for the y. Students tend to solve for y, but I solve for x just to do it a little differently. Show it doesn't matter which one. Now I have a replacement for x, and what I can do is replace the x in this equation with this, and what you'll see is I end up with an equation with just one variable, and everything else is numbers. That means I can solve it. So 5 minus y equals -1. 5 minus 2y equals -1. Subtract 5 from both sides, subtract 5. And I get -2y equals -6, y equals 3 when I divide both sides by -2. So I take that y equals 3 and put it in back here. Now I know x equals 5 minus 3, which is 2, and indeed our solution is again 2, 3. So we've solved this system 3 ways. We solved this system graphically in the very beginning of this video. We solved it with linear combination by adding the two equations together, and that also gets me down to one variable. And then we do substitution. The point of the linear combination or elimination and substitution is to rearrange things in your system so you have an equation that only has one variable, and you can find a numeric value for that variable, and then you use that to find the number that the other variable needs to be equal to. I have this all typed out below, but I just did the same thing here. Just want to make sure I'm done. Yes, so this is what we would have done in class. Unfortunately, we don't have class this week, but the graphing is what I wanted to show you. The linear combination and the substitution, I think you do one of those this week. I also wanted to show you that there are 3 ways to solve the same system of equations. Most of the time, we do not use graphing. Graphing, this is nice. I picked all nice integers and everything works well. So hopefully this and the other lessons provided will help you understand the concept of solving systems of linear equations. Email me your questions.